Welcome everyone. In this module, we are going to focus on reinforcement learning and decision-making systems. I want to begin by slowing down for a moment because this topic represents an important shift in how we think about artificial intelligence. When many people hear the phrase machine learning, they immediately think about prediction. They think about a model looking at data, finding patterns, and then producing an answer. Reinforcement learning asks us to think about intelligence in a different way. It asks, how does a system learn to make better decisions through experience? That question matters because many intelligent behaviors cannot be reduced to one prediction made at one moment in time. In real life, decisions unfold across a sequence. One choice leads to another. One action may create a new opportunity, or it may create a new problem. So when we study reinforcement learning, we are not only studying how systems learn, we are studying how systems act, how they respond to feedback, and how they improve their decisions over time. A simple way to understand the idea is to think about learning by doing. When someone learns a new skill, they usually do not begin with perfect knowledge. They try something, observe what happens, make adjustments, and try again. Over time, patterns begin to emerge. Some choices work better than others. Some actions produce immediate success but create problems later. Other actions may seem less rewarding at first, but they lead to stronger long-term results. That is the kind of learning process reinforcement learning is designed to model. This system, which we usually call the agent, operates inside an environment. It observes the situation, chooses an action, and receives feedback based on what happened. That feedback helps the agent update its future behavior. This system is not simply memorizing instructions. It is learning from the consequences of its own actions. This is why reinforcement learning is so closely connected to decision-making systems. A decision-making system cannot only answer what is most likely, it also has to consider what should be done next. Prediction can inform a decision, but prediction by itself is not the same as decision making. Reinforcement learning brings action into the center of the learning process. One of the most interesting parts of this module is that reinforcement learning forces us to think about trade-offs. A system may need to decide whether to use what it already knows or try something new. It may need to balance short-term reward against long-term benefit. It may need to continue learning even when the environment changes. They are decision-making issues, and they appear in many organizational and technological contexts. For example, an adaptive system may recommend actions, adjust a strategy, control a process, or guide behavior in a changing environment. In each case, the system is not simply reacting once. It is participating in an ongoing cycle of action and feedback. That cycle is what makes reinforcement learning powerful, but it also makes it complex. We also need to be careful not to treat reinforcement learning as magic. The system does not automatically become intelligent just because rewards are involved. The quality of the learning process depends on how the environment is structured, how actions are defined, how feedback is measured, and how success is evaluated. If the reward is poorly designed, the system may learn behavior that appears effective on paper, but is not actually useful or responsible in practice. That point is especially important when we connect reinforcement learning to decision-making systems. Decisions have consequences. In a business setting or in an automated process, the goal is not simply to maximize a number. Let's start with the question at the heart of reinforcement learning. How does a system learn from experience? Reinforcement learning is not built around the same learning pattern we usually see in supervised learning. In supervised learning, the model is trained with examples that already contain the correct answer. The model sees inputs, sees labels, and learns the relationship between them. Reinforcement learning works differently. The system is not simply handed a list of correct answers, it has to learn through interaction. A reinforcement learning system learns by doing something in an environment and then paying attention to what happens next. It makes a decision, receives some kind of feedback, and then uses that feedback to shape future decisions. So the learning process is active. The system is not sitting passively in front of a data set. It participates in a cycle of action, response, and adjustment. This is why reinforcement learning is especially important for decision-making systems. A decision-making system does not only need to identify a pattern, it needs to choose an action. It needs to decide what to do next under conditions that may change over time. That makes reinforcement learning very different from static prediction or static pattern discovery. For example, if a model is only predicting whether a customer may leave a service, that is a prediction problem. But if a system must decide what action to take in response, and then learn whether that action worked, we are moving closer to reinforcement learning. The focus shifts from simply predicting an outcome to improving decisions through experience. Feedback in reinforcement learning usually comes as rewards or penalties. A reward tells the agent that an action moved it toward a desired outcome. A penalty tells the agent that the action produced an undesirable result or moved it away from the goal. But we have to be careful here. Rewards and penalties are not always simple. Sometimes the effect of a decision is immediate. Other times, the effect may appear later. A system may take an action now, but the real value of that action may only become clear after several more steps. That is why reinforcement learning emphasizes sequential decision making. The system is not making one isolated choice and then stopping. It is making decisions across time. Each decision can influence the next situation the agent faces. In other words, the agent's current action can change the environment, and that changed environment affects the choices available later. This is very close to how many real-world decisions work. A choice made today can shape what happens tomorrow. A system may need to accept a small short-term cost to gain a better long-term result. Or it may need to avoid an action that looks attractive immediately because it creates a worse situation later. That is why trial and error matters in reinforcement learning. The agent learns from experience. It tries actions, observes outcomes, and gradually builds a better understanding of which decisions tend to produce stronger results. This does not mean the agent is randomly guessing forever. It means the agent improves by connecting actions with consequences over time. The phrase trial and error is important because it reminds us that learning is not always clean or perfect. Early decisions may be weak. Some choices may fail. Some feedback may reveal that the system misunderstood the environment. But those failures are not meaningless. They become part of the learning process. The agent uses those experiences to adjust future behavior. So when we say reinforcement learning focuses on learning through interaction and feedback, we are really describing a continuous loop. The agent observes the environment, chooses an action, receives feedback, and updates its future decision making. Then the process repeats. Over time, the goal is for the agent to become better at selecting actions that lead to stronger outcomes. This is where reinforcement learning begins to look more like behavior than simple prediction. A prediction model gives an estimate. A reinforcement learning agent develops a way of acting. It learns what choices are useful in different situations. It learns which behaviors should be repeated and which should be avoided. That is why reinforcement learning is so closely tied to intelligent systems that must operate in changing environments. The central principle is straightforward. Learning happens through experience. The system improves because it interacts with the environment, receives rewards or penalties, and uses that feedback to make better decisions in the future. Let's start with the pieces that make reinforcement learning work, and let's treat them as one connected process rather than a list of separate terms. In reinforcement learning, the system is learning because it interacts with something, makes choices, receives feedback, and then adjusts what it does next. That means we need to understand the agent, the environment, the state, the action, and the reward as parts of the same decision cycle. Once those pieces fit together, the whole idea becomes easier. The agent is the part of the system that makes decisions. But it is more useful to think of the agent as an active participant rather than a passive model. It observes what is happening, selects an action, and then has to deal with the result of that action. In a robotic setting, the agent might decide how to move. In a recommendation system, the agent might decide what option to present next. In any case, the agent is responsible for choosing behavior based on the situation it can observe. That situation exists inside an environment, which is the setting the agent interacts with and responds to. The environment is not just background scenery. It is the part of the problem that changes when the agent acts and then provides new information back to the agent. When the agent chooses one action, the environment may respond one way. When it chooses another action, the environment may respond differently. That relationship gives the agent something to learn from. Before the agent can act, it needs some representation of what is going on, and that representation is called the state. The state gives the agent a view of the current conditions at a particular moment. It might include the position of an object, the status of a system, the available options, or any information that matters for the next decision. The important point is that the agent does not make decisions from nowhere. It makes decisions based on the state it observes, and the quality of that state affects the quality of the action that follows. Once the state is available, the agent chooses an action from the options it has. An action is simply something that the agent can do in response to the state. Although the action can look very different depending on the system, it might be a physical movement, a change in speed, a recommendation, a decision to continue, stop, or adjust the process. What matters is that the action is the agent's attempt to influence what happens next. The action connects observation to consequence. After the action is taken, the environment responds, and that response creates feedback for the agent. This is where rewards become central to reinforcement learning. A reward tells the agent whether the action moved the system closer to a desired outcome, while a penalty signals that the action moved the system away from that outcome or produced an undesirable result. The reward does not need to be dramatic or emotional. It is simply a feedback signal that helps the agent judge the usefulness of what it did. This is also where reinforcement learning differs from a system that is only following fixed instructions. The reward does not hand the agent a complete answer key. It gives the agent information about the consequence of an action in a particular situation. Over time, the agent has to learn which actions tend to produce better rewards under certain states. That learning happens through repeated interaction, because one decision is usually not enough to reveal the best strategy. So the full cycle works like this in natural terms. The agent observes the environment through a state, chooses an action, receives feedback through a reward or penalty, and then uses that experience to guide future decisions. The cycle keeps repeating, and each repetition gives the agent more information about how its choices affect outcomes. If certain actions consistently produce stronger results in certain states, the agent can become more likely to choose those actions again. If other actions consistently lead to weak results, the agent can gradually move away from them. The main point is that learning occurs through the interaction among these components. The agent needs the environment because there must be something to act within. The agent needs states because it must know something about the current situation. It needs actions because learning in this framework depends on making choices, not only observing patterns. And it needs rewards because feedback is what allows the system to improve over time. When we analyze reinforcement learning systems, we should avoid treating these terms as memorized definitions. The agent, environment, state, action, and reward form a feedback loop that explains how the system learns from experience. Through that loop, the agent observes, acts, receives feedback, and adjusts, which allows intelligent systems to improve their decisions across repeated encounters with an environment. Let's now move into one of the most important tensions in reinforcement learning, the balance between exploration and exploitation. This idea matters because an intelligent system cannot improve if it only repeats what it already knows, but it also cannot perform well if it constantly experiments without using what it has learned. Reinforcement learning sits in the middle of that tension. The system has to decide when to try something new and when to rely on actions that have produced good results. Exploration means the agent tries actions that are not yet fully understood. The purpose is the discovery. The agent is gathering information about the environment and testing whether better outcomes might be possible. This matters because early in the learning process, the agent usually does not know which actions are best. If it only chooses familiar actions too soon, it may settle for a weak strategy because it never tested anything else. Exploration gives the system a way to learn beyond its current experience. Exploitation means the agent uses what it already knows to choose actions expected to produce high rewards. This is the practical side of learning. Once the agent has discovered that certain actions work well in certain situations, it should not ignore that knowledge. A system that has learned something valuable should be able to apply that learning when it faces similar conditions again. In that sense, exploitation is how the agent benefits from experience. The challenge is that both exploration and exploitation are necessary, but they pull the agent in different directions. Exploration can lead to new knowledge, but it can also involve risk, because the agent may try actions that produce poor outcomes. Exploitation can produce reliable rewards, but it can limit learning because the agent may keep repeating the same behavior even when better options exist. The learning process depends on managing that trade-off rather than choosing one side permanently. A simple way to understand this is to think about everyday decision making. Suppose someone is choosing where to eat. Going back to a restaurant they already know and like is exploitation, because past experience suggests the outcome will be good. Trying a new restaurant is exploration, because the result is uncertain, but it creates the possibility of discovering something better. Reinforcement learning faces a similar problem, except the decision is formalized inside a learning system. In intelligent systems, this trade-off has practical consequences. If an agent explores too much, performance may become unstable because the system keeps trying uncertain actions even when it already knows what tends to work. If the agent exploits too much, it may stop improving because it keeps selecting the same known actions and never discovers alternatives that could lead to higher rewards. A strong reinforcement learning system has to manage this balance over time. This is why exploration and exploitation directly influence the effectiveness of decision-making strategies. A decision strategy that explores at the right time can help the system discover better options, adapt to changing conditions, and avoid becoming trapped in a narrow pattern of behavior. A decision strategy that exploits at the right time can help the system use accumulated knowledge, maintain performance, and act efficiently when the evidence is strong enough. The skill is knowing how to balance them across repeated decisions. This trade-off also reminds us that learning is not only about finding a good action, it is about deciding how much confidence the system should place in what it has already learned. Early in learning, exploration may need to play a larger role because the agent has limited experience. Later, exploitation may become more important because the agent has gathered enough feedback to act with greater confidence. Even then, exploration may still matter if the environment changes or if the system encounters new situations. That point is especially important for decision-making systems because real environments are rarely fixed forever. Conditions can change, preferences can shift, and what worked before may not remain optimal. If a system becomes too rigid, it may continue exploiting an old strategy even after that strategy has lost value. Exploration allows the system to remain open to new information, while exploitation allows it to use the knowledge it has already gained. Together, they support adaptive decision making. When we differentiate between exploration and exploitation, we are not separating a good behavior from a bad behavior. We are identifying two necessary parts of reinforcement learning. Exploration helps the agent discover, while exploitation helps the agent perform. A reinforcement learning model becomes effective when it can balance discovery with performance, uncertainty with confidence, and experimentation with prior learning. Let's now focus on how reinforcement learning models learn optimal policies, because this is where the decision-making purpose of the model becomes clearer. In reinforcement learning, the goal is not simply for the agent to collect feedback after individual actions. That pattern of behavior is what we call a policy, and the quality of the policy determines how effectively the agent can act over time. A policy tells the agent what action to take when it faces a particular situation. In practical terms, it connects states to actions. When the agent observes one set of conditions, the policy guides one choice. When the agent observes a different set of conditions, the policy may guide a different choice. This matters because intelligent behavior is not usually based on one universal action that works everywhere. A good decision depends on the situation, and a policy gives the agent a structured way to choose actions based on the situation it is facing. When we say that a reinforcement learning model is learning an optimal policy, we mean that the agent is trying to discover the pattern of actions that produces the best results over time. The word optimal is important, but it has to be understood carefully. It does not mean the agent is choosing whatever gives the biggest immediate reward at this exact moment. In reinforcement learning, the best decision is often the one that improves cumulative rewards across a sequence of decisions. That means the agent has to consider how an action affects not only the present state, but also the future states that may follow. This is why policy learning is tied to long-term outcomes. An agent might face a situation where one action gives a quick reward, while another action creates better opportunities later. If the agent only cares about the immediate reward, it may choose the short-term option and miss the stronger long-term path. But if the agent is learning a policy designed to maximize cumulative reward, it begins to evaluate actions in terms of their broader consequences. The policy becomes a way of guiding behavior across time, rather than reacting to each moment in isolation. The process of improving a policy happens through experience. The agent tries actions, receives rewards or penalties, and uses that feedback to update its future behavior. Over many interactions, the agent begins to recognize which actions tend to produce better results in certain states. It also begins to learn when an action that seems useful at first may create weaker outcomes later. This repeated adjustment is what allows the agent's behavior to improve. The policy becomes stronger because it is shaped by the relationship between actions and consequences. This also helps explain why reinforcement learning is different from simply programming a fixed rule. A fixed rule tells the system what to do in advance. A learned policy develops through interaction. The system improves because it receives feedback from the environment and gradually adjusts its decision-making strategy. That makes reinforcement learning especially useful in environments where it is difficult to specify every correct action beforehand. Instead of trying to write every rule manually, the model learns which actions are effective through repeated experience. Cumulative reward is the guiding idea here. Each action may produce feedback, but the agent is not only trying to win one step, it is trying to learn a strategy that performs well over a series of steps. This is why an optimal policy is connected to future value. The agent has to learn which choices lead to better overall outcomes, even when the reward is delayed. In many decision-making problems, the most useful action is not the one that looks best immediately, but the one that places the system in a better position later. For decision-making systems, this is a very important distinction. Organizations and intelligent technologies often face choices where the immediate outcome does not tell the whole story. A decision may look efficient in the short term, but create risk later. Another decision may require patience or adjustment now, but produce stronger long-term value. Reinforcement learning gives us a framework for thinking about that kind of decision making because it places long-term performance at the center of learning. So when we evaluate how reinforcement learning models learn optimal policies, we are really looking at how agents improve their behavior over time. The agent observes states, selects actions, receives feedback, and updates its policy so that future decisions are better aligned with cumulative rewards. The policy defines what the agent should do in different situations, and the learning process gradually improves that policy through experience. The result is a decision-making system that does not merely respond to feedback once, but uses feedback over time to develop more effective behavior. Let's finish this module by connecting reinforcement learning to real-world intelligent systems, because the value of this approach becomes clearer when we think about systems that have to adapt through action and feedback. Reinforcement learning is especially useful when a system does not simply need to classify information or predict an outcome. It needs to make decisions, observe results, and improve its behavior over time. That is why reinforcement learning is often discussed in relation to robotics, autonomous systems, recommendation engines, and decision support technologies. Robotics is one of the clearest areas where reinforcement learning makes sense because a robot must act inside a physical or simulated environment. It may need to move, avoid obstacles, adjust its position, or complete a task under changing conditions. In that type of system, intelligence is not only about recognizing what is present, it is about choosing an action that helps the robot operate more effectively. The robot learns by connecting its actions with the results they produce, and that connection allows its behavior to improve through repeated interaction. Autonomous systems depend on this same general idea. An autonomous system has to operate with some degree of independence, which means it cannot wait for a human to specify every action in every situation. It needs a way to respond to changing conditions and adjust based on feedback. Reinforcement learning supports that process because it gives the system a framework for learning from its own decisions. The system acts, receives information about whether the action was useful, and then uses that experience to guide future behavior. This is what makes reinforcement learning different from static automation. Fixed rules may work when conditions are predictable, but intelligent systems often operate in environments where conditions shift. If the system is going to remain useful, it needs some capacity to adapt. Reinforcement learning helps create adaptive behavior by linking actions to feedback and allowing the system to improve its decision-making strategy over time. Recommendation engines provide another useful example because they also involve repeated decisions. A recommendation system does not only present one option and then stop. It may continue learning from user interactions, preferences, selections, and responses. Each recommendation can be treated as an action, and the feedback can help the system understand whether that action was effective. Over time, the system can improve future recommendations by learning which choices create better outcomes. This connection to recommendation engines is important because reinforcement learning is not limited to physical movement or robotics. It can also support digital decision making. In many intelligent systems, the action may be choosing what content to show, what option to suggest, what process to prioritize, or what decision path to follow. The environment may be digital, organizational, or user-driven, but the pattern remains similar. Decision support technologies also benefit from reinforcement learning because they often operate in complex environments where the best action is not obvious. A decision support system may need to evaluate changing information, compare possible actions, and recommend a course of action based on expected long-term results. Reinforcement learning is useful here because it emphasizes cumulative outcomes rather than immediate results. The system can learn which strategies produce stronger performance across repeated decisions. That long-term perspective matters because real-world decisions often involve consequences that unfold over time. A choice that looks effective immediately may not be the best choice later, while a choice that seems less rewarding at first may lead to better future outcomes. Reinforcement learning gives intelligent systems a way to evaluate behavior through this broader lens. It helps the system learn from feedback across time. Across all of these applications, the common theme is adaptive and intelligent behavior. Whether we are discussing robotics, autonomous systems, recommendation engines, or decision support technologies, reinforcement learning provides a structure for improvement through interaction. The system does not have to begin with perfect knowledge. It can learn from experience, adjust its behavior, and become more effective as it receives feedback. So the real-world importance of reinforcement learning is that it gives intelligent systems a way to make better decisions in complex environments. It supports systems that must act, learn, adapt, and improve over time. That is why reinforcement learning is such an important part of decision-making systems, and it is why the concepts in this module matter. They help us understand how artificial intelligence can move from prediction toward adaptive action in real-world settings.